Chem 201, College Chemistry 1. This time we're with Chapter 3, titled Stoichiometry. Stoichiometry is very heavy in calculations. Okay, so this one might be the first time we're going to be exposed to numbers, quantities. This is really the heart of chemistry. Normally, chemistry is associated with, well, chemical reaction, industry, right? How much of a particular reaction, right? So you're going to be producing, how much product, how much do you need your reactants. So that is really the domain of stoichiometry. Anytime that they tell you stoichiometry is always referred to quantities, right? So there is even a field in chemistry which is called analytical chemistry. Analytical chemistry is not other thing that the expanded version of chapter 3 of this class of chemistry 1. Okay? So this is an overview of all the topics that we will see. You can see like counting and weighing, atomic mass, small mass. So definitely for this chapter, we're going to use a lot of our calculator and also the periodic table, mostly for the last part, because here in the last part is where you're going to determine the for a particular chemical reaction. Okay, let's get started. So the definition for stoichiometry is, as I said before, is the study of quantities of materials that are consumed in a chemical reaction. Okay, so we are talking only about chemical change, nothing about physical change. Remembering in physical change, you don't produce new substances. So only in chemical change, that's why here we have to highlight that it's about chemical reactions. Anything that is involved in a chemical reaction that involves a reactant and a product is the subject of a study of stoichiometry. Okay? Stoichiometry is not another field of chemistry. So it's not like organic, analytical, physical chemistry. No, stoichiometry is just a chapter. It's a section that is studying chemistry. You can do stoichiometry in organic. You can do stoichiometry in physical chemistry. You can do stoichiometry in analytical, in environmental, in instrumentation. You can do stoichiometry anywhere you want. Okay? So the first part of the quantification is how to determine the molar mass. I don't know if you guys remember, but when we were trying to determine, let's say in this case, we have carbon, right? So you go to the periodic table, you will see that carbon, it says 6, which is the atomic number. But on top of it, you will see that there is a number that says 12 point, right? If you go to the periodic table, 12.00, sorry, 0, only 1 0. 115, and this 115, I mean this number from the periodic table is called the atomic mass or atomic weight, right? So some of you might think like, oh, that's the same thing of mass number. Mass number is A, right? The A number. No, because it comes from a collection, right? It is really a correlation between the abundance of the isotopes, right? So these are the isotopes: carbon 12, carbon 13, and carbon 14. You can see how they're distributed in nature. Okay? So carbon is not only one single element. So it really has like a family of elements inside. They all have six protons, right? Because it's 6 here, 6, 6, and 6. I mean, they're all carbon atoms. The nucleus has 6 protons, but the number of neutrons is different. So they have the same number of protons, but different number of neutrons. That makes them isotopes. But it would be really unfair to determine the weight of carbon only based on the most abundant. That's why in chemistry, we were saying, in chemistry, it would say like, okay, since it's unfair to only give a weight based on the most abundant, why don't we get a correlation, right? Or the average of the atomic mass for carbon? That's exactly what we're trying to do here. So they determine that the atomic mass of the isotope carbon 12, right? So this is C12. C12 is 12 AMU. What is AMU? AMU is atomic mass units, right? Atomic mass units. That's the weight of an atom of carbon. So, and then the abundance is 98.89. The second isotope, which is carbon 13, right? Carbon 13, the weight, right, or the atomic mass is 13.0034 AMU, which is atomic mass unit. And the percentage is 1.11. Why are we not considering carbon-14? You say like, what happened with carbon-14? In this particular case, they don't consider it because if you see, it's very small, right? So it is carbon-14 is less than 0.04, 0.01%. So that's why maybe they neglected it, and then they didn't consider here carbon-14 because of this small percentage. Okay? And then they do the calculation. I mean, the percentage is transferred or is converted to decimal, right? The 1.11 is also converted to decimal, and then they get the molar mass of carbon. You can see 12.01, which is exactly what we see on the periodic table. Okay? So even though natural carbon does not contain a single atom with mass 12.01, which is true, but it's an average. So you are prorating, right? So you're extrapolating, you are getting an average of the isotopes. So how do we confirm? How do we know that isotopes really have those masses, right? Because you would say like, so how do you know, or how in chemistry, how do chemists know that carbon-12 weighs 12, carbon-13 weighs 13? Is that because it's 13? How do you really confirm that 13 is really the mass of that isotope? Well, there is an instrument which is called the mass spectrometer. That one, for the ones that are doing forensic science, you guys will have the opportunity to see this in a deeper detail in the instrumentation class. A mass spectrometer is an instrument that allows you to determine the weight of a particular sample, but not the weight as a balance. It's the weight of the molecules, the atoms that are part of your sample. Okay? So the instrument, the structure, the scheme is very simple. So you put the sample through a machine. Like normally you put it in a plate. Yeah, you don't inject. Well, sometimes you can inject it, but most of the time you do the ones that are only mass spectrometers is a plate that has a sample. The sample is pushed through a tube, through a tunnel, and then that tunnel, what it's going to do is gonna apply electrical field. In some cases it's electrical field, some cases is light, some cases is X-ray. Here, as you can see, electron beam, right? So electrical, magnetic fields, different types. So the purpose of that is that you have your molecule here, let's say, and then you break it into pieces, you fragment it. Okay? So what you will have, it will be pieces of fragments of your molecule. So since the molecule is at a very high speed, because this one is going to be passed through a tunnel, it applies magnetic field, and that magnetic field definitely will go, and then it will start flying. Okay? So something that is very heavy, right? Obviously, it's going to take longer time, right, to travel. Something that is very small, it won't take, it will just fly quickly, right? So with the magnetic field, these guys are all positively charged. Why are they positively charged? Well, because you are shooting in them with electrons. So definitely you're going to be losing electrons somewhere. Okay? That's good. That's going to be deeper in, whenever you guys take mass spectrometry. Okay? So positive particle, negative particle, what's the difference between those two? The weight, right? The weight is going to be different. The larger is definitely going to take longer. And the smaller is going to take, doesn't take too long to fly. So they fly all this tunnel here. You can see they fly all the way. And obviously the heavy ones are going to take longer. The light ones are going to take shorter time. So that is the foundation. So obviously you will have fragments, but not everything is going to be fragmented. You will always have your molecule that doesn't get fragmented. So you will get a spectrum with peaks. Right? Let's say like this one is your peak for your molecule, but then you will get also other peaks. Those are the fragmentation patterns. Right? That's a fragmentation pattern for a particular molecule. Let's say that you have nitric acid, HNO3. Right? So in HNO3, you will have the weight, the total weight of HNO3 is going to be right here. That peak will contain information for HNO3 because that's the highest peak. But what happens if I break it, fragment it, and I lose hydrogen? Then I will have only the weight of NO3. Maybe NO3 is right here. Or what if I lose an oxygen? Well, if you lose an oxygen, you have something lighter right here. And then you lose a nitrogen and an oxygen, you get, so different fragments, they will have different weights. Okay? So then, since the mass spectrometry has been around for so long, that is how, the chemists, they have come up with a library. So if you have a molecule that has this fragmentation pattern, that should be nitric acid. This molecule has this other fragmentation pattern. You check the library. Oh, that fragmentation pattern belongs to caffeine, let's say. So that's how they determine if a particular molecule is caffeine, is aspirin, or is ibuprofen, or is penicillin, azithromycin, any drug you can see through mass spectrometry. Okay, so this is an exercise. Let's do that by hand. Again, we will do this type of problems more on the other videos, right? An element X, I will call it, consists of 62.20% of an isotope. The isotope has the mass of 186.956, and the other AMU, and the other isotope is 37.40 with a mass of 184.953 AMU. Okay, I'm going to do this problem right here. Okay? So we have the element is X. This element has two isotopes, right? You can see the isotope with 62% and then 37%. Right? So in this case, I have one isotope. So for this would be 62.60 times the mass, 186.956, right? Plus the other contribution, because the other isotope contributes. Even though it's smaller, only 37%, but it's still a decent contribution. So you cannot really neglect it. Okay, so here we can, since this is percentage, right? 62 is a percentage, so 62.60 divided by 100. So this is really a fraction, 1.626, right? I'm just converting percentage into decimals, times 186.956 plus 0.374 times 184.953. Right? Remember, no sig fix here. So here, from this line to this other line, all I'm doing is just converting percentage into a fraction, right? Into a decimal. Right? So 0.626 times 186.956. This part is 117.03. I'm cutting the number to the second decimal place. If I need to round it, I round it, but in this case it's a 4, so I don't round it. Plus 0.374 times 184.953. So 69.17. So 69.17 plus 117.03, the molar mass, I mean the weight of that particular isotope is 186.2 AMU. Okay? So that's what my calculation is throwing. So let's double check. 186.2 AMU, exactly what I was, right? What we were calculating. That's the average atomic mass. In this case, it's rhenium. Well, is there any way how you can determine that it's rhenium? Well, you will just have to navigate the entire periodic table to see which element has that atomic mass, right? Yeah, I'm just looking right now at the periodic table, and exactly 186.2 is rhenium, Re. Okay. Let's continue. Okay, so now let's go to the concept of mole. Mole is a very important topic. Okay, so I'm gonna stop the video, I mean the PowerPoint. So here, the definition of mole is very important for us to understand what is a mole. Mole is really a unit, it's a quantity of mass, okay? But okay, of mass of a particular substance. So imagine you have 1 gram of cotton. Okay? What is it gonna be 1 gram of cotton? Let's say like this much. You have 1 gram of lead. Maybe 1 gram of lead is gonna be maybe a marble of lead, right? Or a cube of lead. What about if I have 1 gram of hydrogen, right? 1 gram of hydrogen is gonna be a tank that has a lot. So you can see that the representation, you can definitely see I weigh 1 gram of cotton. is like a lot, right? In volume, occupies a lot of space. But if lead, no. In hydrogen, even more, because hydrogen is a gas. So how can I say like it doesn't really represent the amount of matter that is in 1 gram. So I cannot really say like, oh, 1 gram of cotton is equivalent to 1 gram of lead. No, right? Because lead is really dense. It's really, I mean, all the matter is compacted in that small particle or small object. Cotton, no. Hydrogen, even worse, right? So that's why they came up with the idea of mole. So we cannot really go by the mass, because an atom of lead, right? If we go to the periodic table, an atom of lead has how many protons? An atom of lead has 80 lead. Lead has 82 protons. What about the atom of hydrogen? The atom of hydrogen only has 1 proton. So definitely 82 protons are going to weight, right? Way more than 1 hydrogen. And for cotton, well, cotton is really not an element, it's a molecule, normally has cellulose, right? Cellulose is a polymer. So let's just leave that on the side. But just using this comparison is like hydrogen, 1 proton, 82 protons for lead. Definitely this is gonna weight way more than this. So if I say 1 gram and 1 gram, it's totally unfair for me to compare these two based on the grams, right? So that's why they came up with the number of moles. Mole is really a quantity that compares like the number of lead atoms, right? Versus the number of hydrogen atoms here. Now we are in equal conditions. If I have 10 atoms of lead and 10 atoms of hydrogen, now we are in equal conditions. So really the mole, it is a quantity. So the quantity, what it really stands is like what is the weight, right? In grams, of course, right? What is the weight of grams that is contained in a given number of atoms, right? So you would say like, oh, well, do we use 10 atoms? 1 mole represents 10 atoms? No. There is a guy later, came Avogadro. Okay. Avogadro was a scientist that was working on the, where's my eraser? When I need my eraser, I don't have eraser. Well, Avogadro came up with this type of, this idea of here, Avogadro came up with this idea that 1 mole of any substance contains 6.023 or 22 times 10 to the 23 atoms. Okay, so he found that out from the carbon atom. Okay, so let's go again to share the screen. Okay, so as you can see here, it says like 1 mole of anything contains like, the number of equal, right? The number equal to the number of, the number of carbon atoms is exactly 12 grams of pure carbon 12. So he did his experiment with carbon 12. So he used carbon as to study okay? So he used the carbon as the element for him to study. So he determined that 1 mole of, well, he generalized it afterwards, but 1 mole of anything, so let's say 1 mole of lead, contains 6.022 times 20 times 10 to the 23rd units of that thing. That he called that the Avogadro's number. For example, 1 mole of carbon contains 6.022 times 10 to the 23 carbon atoms. That has a weight of 12.0 of carbon. Okay? So let's just go to the, okay? So basically what he did is he said like, okay, so in this particular, let's say this is graphite. Graphite is the like graphite is the, well, let's say, let's do a different thing. Diamond. Diamond is pure carbon, right? So pure carbon has, let's say, in this case, he determines this one is 6.02 times 10 to the 23 atoms of carbon. So he will call this is 1 mole of carbon. Okay, and what is the weight of 1 mole of carbon? Well, the weight of 1 mole of carbon is 12.01 grams. Okay, so now we're not talking about AMUs. Remember, the weight of one atom of something, that's the one that is given in AMUs. The weight of 1 mole of something, it is given in grams. Okay, so, and then one mole of something contains 6.022 times 10 to the 23. Okay, so that applies to anything. For example, what if I don't have atoms? I have molecules. Right? Because we know from the previous chapter is that I don't need to have pure lead. What if I have lead oxide, right? Lead oxide, lead 4 oxide is a molecule. How does that translate into the Avogadro's number? Well, now in this case, you will say that you have 6.022 times 10 to the 23rd molecules of lead oxide, okay? So 1 mole of PbO2, right? Lead 4 oxide contains 6.02 molecules. What about electrons? I have 1 mole of electrons. So you have 1 mole of electrons, you will say that you have 0.02 times 10 to the 23 electrons, right? So as it says in the slide, like 1 mole of something contains 6.022 times 10 to the 23rd something, right? So, or particles of that something. In this case, it's electrons. 1 mole of electrons contains this number of electrons. 1 mole of molecules contains this number of molecules. 1 mole of atoms, right? Carbon atoms contains Avogadro's number atoms. Right? So this is a number that definitely has to stick to you. I mean, we don't see it in quantification that much because normally nobody says, oh, give me 5,000 atoms of lead. No, nobody says that, right? So normally you say like, give me 5 grams or give me 0.5 moles of lead. That is more common to say. But we still have to study the Avogadro's number. Okay? So in this case, now let's see, calculate the number of iron atoms in 4.448 moles sample of iron. Okay, so let's do that. Let's see, number of iron atoms. Let me write the data in a 4.48 mole sample of iron. Okay. So we know that iron, the symbol for iron is Fe, right? So here it says like, I want to determine the number of iron atoms in a 4.48 sample. So I know this is a new, now I know that this is a new conversion factor. 1 mole of something contains 6.022 times 10 to the 23 something, right? So for example, 1 mole of atoms here too. 1 mole of molecules here too. Electrons here. Protons here, right? So in this case, I want to convert that 4.48 moles of iron atoms, right? Times that conversion factor. 1 mole of iron atoms contains 6.022 times 10 to the 23 atoms of iron, right? So moles of atom, right? Moles of iron atoms, moles of iron atoms cancel out. So I have to multiply now 6.022 times 10 to the 23rd times 4.48. The calculator throws 2.70 times 10 to the 24 atoms of iron. That would be my answer. Okay, I found my eraser. Good. Okay. So that would be the answer. So you have to determine, I mean, the number of molecules. There are some more, again, we will have more examples. For For example, under videos, right? My salt videos, I always post on Blackboard. There are some other cases. Let's say that you have how many atoms, right? Right? How many atoms, right? In this case, how many atoms of iron, right? Do you have in let's say 5 moles of iron 3 oxide, right? This question says like, how many atoms of iron do you have in 5 moles of iron 3 oxide? So this one is a bit more complicated because now we're talking about a molecule. They don't want me to determine how many molecules of this I have. They want me to determine how many atoms of iron are inside of that molecule. So that's a little bit more complicated. So let's see. First, I have to find out how many molecules I have in 5 moles. So 5 moles of 5 moles of, right? Here I use the Avogadro's number, 6.022 times 10 to the 23 molecules, right? In 1 mole of molecule, okay? Times, well, 1 mole, not just 1 mole. I would say 1 mole here only. Can I say 1 mole of molecules? Yeah, I can say 1 mole of molecules, but yeah, just I cancel out here. But now I also know that one molecule of iron 3 oxide contains 2 atoms of iron. Okay? So 1 molecule of iron 3 oxide contains 2 atoms of iron, right? How do I get these 2? Because the formula says 2, FeO3. If they ask me for oxygen, well, I would say there are 3 atoms of oxygen, right? So these 2 comes from this number. Each molecule of this oxide contains 2 atoms of iron. So if I cancel out, if I do the calculation, I will see moles of iron oxide, moles of iron oxide, molecules of iron oxide, molecule of iron oxide. My answer is going to be in atoms of iron, which is exactly what I want, right? The question is asking me for the atoms of iron. So, so let's see the calculation. So 5, I prefer to start with the Avogadro's number, times 2 times 5. Well, not much change, it's just the power. That would be my answer, right? 6.022 times 10 to the 24th, right? So that's atoms of iron. See, so there are different ways how to convert things. I mean, using the Avogadro's number. It's not necessarily, they are not gonna be asking you directly, right? So I have a molecule, I want to determine the number of molecules. No, I mean, that would be very straightforward. Or a mole of atoms, I want to determine directly the number of atoms. No, that would be a simple conversion like what we did here. That was a simple conversion. But most of the problems, they will ask you to have this. For example, a very, like a molecule, and then inside the molecule, they want to determine the number of atoms that are inside. Okay, so once again, we will do more of these problems on the for the YouTube videos. So let's double check here, 2.70. Yeah, that's exactly what we got in our calculation. I mean, you can go back on the video to see that you have that number of atoms of iron. Okay, molar mass. Molar mass is the mass in grams of 1 mole of the substance. Okay? So for example, we get that from the periodic table. So normally we get up to the 2nd decimal place, but to be honest, most of the elements are like this, most of them. Okay? So can I disregard that 0.1, this 0.2? Yes, you can disregard that. So in other words, if they tell you what is the molar mass of the atomic weight of nitrogen, you will say just 14. Okay? because it doesn't make sense to, I mean, 0.1. With the exception of two elements, copper. Okay? For example, copper, if you go to the periodic table, you will find out that copper weighs 63.54. So in that case, I cannot neglect, I mean, I cannot really ignore that 50, the 54. So I would use the 50, or you can even do 5, right? 63.5, that counts. The other one that is going to be also very common for us is chlorine. Chlorine is another element, 35.5, right? So in this case, I don't recommend you to round it. Don't round them because it's, well, 35.45, but you can round it to 35.5. Okay? So in this case, you cannot round it, but there are some other elements, the majority of the elements, for example, sodium is 22.98. 22.98 is 23. Lithium, 6.9. Definitely, I will count it as 7. Oxygen, oxygen is 15.999. Yeah, I will say is 16. Fluorine, 18.998. Yeah, I will round it to 19. Right? So just round it as you guys think that it would be the closest in value. Yep. So let's do one easy example. For example, this molar mass of barium nitrate, which seems to be like a kind of complex molecule. So I think it could be a good example for us to do. Let's do the, according to this is 261.35 grams per mole, right? So let's do that. Let's do that, how it is done on the paper. Okay, so what we are gonna determine now is the molar mass, which you can also call it molar mass, mm. Some other cases you will see the M with a bar, that's the abbreviation, or you will also say molecular weight. That's another way how to call it. Okay? Molecular weight, molar mass, mm, M with a bar. That's the units are always grams per mole. Okay, so is the number of grams that are containing 1 mole of the substance. So in this case, I will just break that up. I mean, I will break up this this molecule. How many baryons do I have? 1. How many nitrogens do I have? The nitrogen here have a 1, but this nitrogen is inside of this parenthesis with a 2. That means that I have really 2 nitrogens. Oxygens, how many oxygens do I have? I have 3, but the 3 is inside of the parenthesis, right? 2 times 3 is 6. What is the weight of each barium? Barium weighs 137.3. Can I neglect it or can I ignore that? Yes, in this case, yes. Okay, so each barium weighs 137. Okay, nitrogen, I have 2 nitrogens. What is the weight of nitrogen? Nitrogen weighs 14.00. Okay, ignore the decimals, 14. Oxygen, 6 oxygens, and then each oxygen is 16. Multiply this 137, this is 28, and this one will be 6 times 6, 36, 96, right? You add this up, that will be 15, 21, that will be, I can add 6, right? 261. Okay? That would be mine. And then what they was giving was 261.35, close enough. What is that difference? Well, it is because I didn't count the 30, right? For the barium, I didn't use that. But 261 is close enough. So I would say 261 grams per mole. Okay? Let's do another one more, a little bit more complicated. Let's see, what can we do? Let's do something that you also have to use the parenthesis. Ammonium phosphate. Okay, ammonium phosphate. Yeah, that's a good example. They tell me what is the molar mass of ammonium phosphate. So I have to list all the elements. I have nitrogen, I have hydrogen, I have phosphorus, and I have oxygen. I have to determine how many of each do I have. Nitrogens, how many nitrogens? Here I have 1, but it's inside of the parentheses times 3. That means 3 nitrogens. Hydrogens, 4. 4 times 3, 12, right? The parenthesis is multiplying, always multiply the number of atoms that you have as a subscript. Phosphorus, only 1. Oxygens, I have 4. There is no parenthesis, therefore I don't multiply it for anything else. Nitrogen, if you go to the periodic table, nitrogen is 14. Hydrogen, always 1. Phosphorus, I go to the periodic table, is 31. Well, it's 30.9, 30.97, so I could say that it's 31. Oxygen, from the previous example, we know that is 16. 3 times 14, that is a 42. 12 times 1, 12. 31 here. 16 times 4, it is 64. Right? Add this, 8, 9, 9, 10, 14. So the molar mass or molecular weight of ammonium phosphate is 149 grams per mole. Okay? Why is this important, right? Molar mass or molecular weight, because it allows you to go from grams to moles. Right? That is a conversion factor you're going to be using, because you can see here it combines these two units, grams per mole. So it allows you to convert easily from mass to moles, which makes sense, because normally when you go to a let's say like chemicals, right, store, you don't say anybody, oh, can you please give me 10 moles of lead? No, you normally say like, give me 10 grams of lead, or one pound of lead, right? So there's definitely something that you have to consider, that moles applies for chemical reaction. Chemical reactions, we're going to be using moles a lot. But when you buy in, you know, in life, in real life, I mean, you never say like, give me 10 moles, please buy one, you know, like 25 moles of lead. No, whenever you go to the store, you always say like mass. So you always have to be aware of this conversion, that you have to do a conversion back and forth. Whenever you do a chemical reaction, go with moles. But in real life, you're gonna work with moles. You really have to work with grams, pounds, kilograms, right? So that particular unit. But that's why it's very important to use this molar mass concept, molar mass idea. Okay, so let's go back to the presentation. Okay. That's exactly what we did. Rank the following according to the atom numbers. I mean, rank the following according to the number of atoms, the greatest to the least. This is only a way. We can do this. I mean, we do more problems later, but 17.9 grams of silver, 70.0 grams of zinc, 21.0 grams of magnesium. Okay? So they tell me which one has the largest number of atoms, right? So in this case, well, I know that one mole of something contains 6.022 times 10 to the 23 something, right? In this case, these are all atoms, so I could say atoms here. So what is the best way how to determine if I have more particles or more atoms? Well, convert everything into moles. I would say like each of these guys, convert them into moles. How can I convert this into moles? By using the molar mass. For example, if I want to convert 107 grams of silver, I use the atomic mass of silver. Silver is 107.9, exactly, right? You can see that here. So 1 mole of silver weighs 107.9 grams of silver, of course, right? So grams of silver with grams of silver cancel out. So 107 grams, so I have 1 mole. So this 107 grams is really 1 mole. That means that in that many grams, I have exactly 6.022 times 10 to the 23 atoms of silver. What about zinc? In the case of zinc, 70 grams of zinc, right? What is the molar mass of zinc? I go to the periodic table, the molar mass of zinc is 65.4. Okay, so 1 mole of zinc weighs 65.4 grams of zinc, right? Grams of zinc, grams of zinc. If I do this division, 70 divided by 65.4, 1.07. So in this case, I have 1.07 moles. right, of zinc. And the last one, magnesium. For magnesium, I have 21 grams here of magnesium. And according to the molar mass, 1 mole of magnesium weighs 24.3. Okay, cancel out. 21 divided by 24.3, 0.86. Okay. Okay, now that I have everything in moles, then I can make the comparison. A mole contains this many atoms. Here I have 1.07, so definitely zinc is going to win. So where do I have more atoms? I have more in zinc, and then I have in silver, and then last in magnesium, right? Because of the number of moles. Remember, the more moles you have, the larger is going to be the number of the particles, right? Because 1 mole contains 6.022 times 10 to the 23rd. Okay? So if we go to the answer, I mean, it should say it better. Right? Yes, zinc first, then is silver, and then it is magnesium, right? Because here it says magnesium, that's the C, right? Zinc is the first one, which is a Google calculator, and silver is letter A, is the second one, right? Exactly with 1 more. Good. So now let's say, what are we going to do? We're going to be dealing with chemical reaction, okay? So at any time that you are going to read a chemical reaction, you always have to read the problem, decide on the final goal. So it's very important that you understand the problem. You're going to be giving information. It cannot just ask you out of the blue for a particular weight or mass or number of moles if you're not giving some ground data, right? So you need to work on the ground data, see what you have, and also see what they're asking you for. Okay? How do we get there? So here, that's the point, is that you have to determine like what is my end goal? So am I going to determine the number of atoms? Am I going to determine the number of grams of a chemical reaction? Am I going to determine a formula, right? So, or percentage, right? So that's really, I mean, what you always, whenever you're in front of this particular problem, so stoichiometry, always have to be, sit down and then always see what you are giving and what we are asked for. The first one is the percent composition of compounds. I mean, we're going to go deeper in calculations. Mass percent of an element. For example, iron oxide. What is the percent of iron in iron oxide? That's a simple conversion. So here is, okay, let me see. Consider a separate 100 gram sample of each of the following, right? Rank them from highest to lowest percent of oxygen by mass. Okay, so I have 100 grams of water, dinitrogen monoxide, C3H6O2. What is that? That looks like propionic acid, carbon dioxide. Okay, so they want me to run them based on the percent in oxygen. Okay. Percent oxygen. I'm assuming 100 grams, right? So 100 grams of sample. Do I have to be told 100 grams of sample? No, you can assume that 100 grams of sample. You don't have to be told, right? So here we have to get the percentage, right, of water, percent of oxygen. So how do I get the percent composition in water or oxygen? Well, first I have to get the mass of the element in question. In this case, it's oxygen. What is the mass of oxygen? 16, right? 16 grams. Divided by the total mass. What is the total mass of that? Is that the 100 grams? No, this is not the mass. That's the mass of the sample. Remember, you are looking at the molecule. What is the percentage of oxygen? What is the contribution of oxygen in the entire water molecule? In this case, I have to determine the molar mass. If you get the molar mass of water, the molar mass of water, you have 2 hydrogens and 1 oxygen. 2 hydrogens, 1 oxygen. Each hydrogen weighs 1. Each oxygen weighs 16. The molar mass is 18 grams per mole. Okay, so 1 water molecule weighs 18 grams, right, of water. But inside of that 18 grams of water, 16 belong to oxygen. So that is my proportion, and then times 100, right? Because I'm getting the percentage. 16 divided by 18 times 100. 88.89. Okay, that's the percentage of oxygen in water. Let's do it now for nitrogen, dinitrogen monoxide. Weight of oxygen, 18 grams, right? That's the same for all of them. Now, what is the total mass of this particular molecule? Nitrogen, 1 nitrogen is 14, but here I have 2. That means that it's 28. 28 plus 16 is equal to 44. So it's 44 grams of dinitrogen monoxide. Well, the 44 is just coming from my molar mass, right? I'm just doing it quickly here. We have done it a couple of times already, so we can speed up the process. Okay, 16 divided by 84 times 100, 19.4, 19.04%, right? Well, 0.5, 19.05. Yeah, just run it the second decimal place. Next, I have, next one is C3H6O2, right? In this case, how many grams of oxygen do I have? Here I have two oxygens. Each oxygen is 16. 16 times 2, 32. 32 grams of oxygen. Divided by the total. The total is going to be the molar mass. Okay, let's do here quickly the molar mass. Carbon, the mass of carbon is 12. 12 times 3, 36. Hydrogen, each hydrogen weighs 1. 1 times 6, 6. Oxygen, each oxygen weighs 16. 16 times 2, 32. This plus this should be equal to, let me see. This one will be 42. 42 plus 32, that would be 74. So the total is 74 grams of the total, right? Total. So 32 divided by 74 times 100, 43.24%. Okay. And the last one is carbon dioxide. Carbon dioxide, how many grams of oxygen do I have in carbon dioxide? I have 2 oxygens. 2 oxygens. Each oxygen is 16. 16 times 2, 32. 32 grams of oxygen. The total carbon, I have 1 carbon. 1 carbon is 12, right? 12 times 1, 12. Oxygen, each oxygen is 16. 16 times 2, 32. The molar mass is 44. So 32 times 100 divided by 44. 72.73%. Okay, so these are my percentages. For water, 89%. For nitrogen, dinitrogen monoxide, 19. For this organic compound, I have 43%, and this one is 72. So for me, I would say like water has higher oxygen percentage than carbon dioxide. Carbon dioxide has more oxygen percent than C3H6O2, and the last one would be dinitrogen monoxide, right? So that would be my ranking for oxygen percent for this particular problem. Let's see what they say, which I think should be water, carbon dioxide, the acid, and dinitrogen monoxide. Okay. Okay, formulas, empirical formula. Once again, we're going to be very heavy calculations today. So empirical formula is one way how you can express a formula. Okay, so is there any way how I can come up with a formula if I'm given the percentages? Yes, right? So for example, if I tell you a molecule has 50% carbon, 30% nitrogen, and then 20% hydrogen, can I figure out what is the formula? Yes. So that is exactly what we're going to do right now. So determining the formula of a compound based on the percentage. That's why we did percentage right before the empirical formula. So empirical formula is the minimum, as it says here, the simplest whole number ratio. So CH will be the empirical formula. So for example, if I have something here, like, let's say like C3, H6, right? So that's a formula. Yes, that's correct. But is that the empirical formula? No, because this number can be simplified. If I take thirds, right, that would be 1, H2. This is the empirical formula, the minimum expression. So the smallest number that you can reduce a particular molecule, that would be your empirical formula. Then what is this? What is the C3H6? The C3H6, it is what we call the molecular formula. Okay, it's right here. It's the real number, right? So should we really pay attention to the empirical or to the molecular? To the molecular, because the molecular is the one that really has all the real number of atoms. But can I get the molecular formula directly? No. From percentages, what you will get is the empirical. And from the empirical, you will go to the molecular. Okay, so I'll show you step by step how this is done. Molecular formula is C6H6, right? This is a known solvent, very toxic, by the way. It's called benzene. Benzene is the formula is C6H6, but that is the molecular formula. What is the empirical formula? The empirical formula is CH, because if I take 6 and 6 here, right? So I get C1H1. That would be the empirical formula. But the molecular formula is really C6H6. So that's the difference between molecular and empirical formula. It's the actual formula of the compound. So for your calculations, obviously you have to get molecular, but you cannot get molecular directly. You have to get first empirical and then molecular formula. How do we get these percentages? There is also an instrumentation for the ones doing forensics, on that later on for the ones that are going to be doing chemistry or analytical chemistry in the near future. There is a technique which is called elemental analysis. Elemental analysis is really like an oven, it's a furnace, right? It's an oven where you are putting your sample, basically you're burning your sample, and then the burning creates gases, right? And those gases are gonna be filtered out by using different types of absorbents. So for example, here you will have an absorbent for carbon dioxide, water, and oxygen. There are some other absorbents that are maybe for nitrogen gases. So your absorbents will absorb those gases that are produced by your sample. So your sample definitely is going to be producing different gases. Those gases are coming from where? Well, those gases are going to be coming from the composition. They will have carbon, hydrogen, oxygen, and nitrogen, right? If this is an organic sample. If you have an inorganic sample, let's say you have lead, iron, zinc, copper, vanadium, chromium. So in that one, you don't produce gases, but you produce are solids. So in the solids, you have to do a different technique. Okay? But in general, whenever we do empirical formula, we always deal with organic samples. So the organic sample treatment is this way. Okay? So you just burn it, and then you just put different absorbents. Those absorbents will take out the gases that are produced in your sample, and then you can determine indirectly the percentage, the percent composition of your particular compound. Okay, so we have adipic acid is 49. We're gonna start the camera in a second, but I need to write the data. The composition of adipic acid is 49.3% of carbon, 6.9% of hydrogen, and 43.8% of oxygen. It's important that you read this, that is by mass. It has to be by mass. Well, it's always going to be by mass. And the molar mass of your adipic acid is 146 grams per mole. So most likely what you guys will do in front of this problem, I'm sure that you will just immediately Google what is the formula of adipic acid and skip all this all this long problem. But I mean, yeah, theoretically yes, but let's see how this is done. I mean, in practice. So please don't Google it. Just let's take some time to do the actual experiment. So the practice. So I have the percentages right from the problem. This is adipic acid has this percent composition. So what I'm going to do is I'm going to divide them by the molar mass. So I'm going to be working first with carbon. I have hydrogen, 6.9, and oxygen, right, 43.8. Okay, so I'm going to divide each of them by the molar masses. Carbon divided by 12, hydrogen divided by 1, and oxygen divided by 16. Once again, what is this? These are the molar masses. Divide them by the molar mass. How do I get the molar mass? Periodic table. Periodic table is going to be your friend from now on. Okay, so divide them. So I'm going to do 49.3 divided by 12, 4.11, 6.9 divided by 1, 6.9, 43.8 divided by 16, 2.74. Okay, so now what should I do? Then you're going to divide them all by the smallest. Who is the smallest? 4, 6, or 2? 2 is my smallest. 2.74, 6.9 by 274, and 4.11 divided by 2.74. All of them by the smallest. Okay? So first divide them by atomic masses. Okay? First. Then you're going to divide by the smallest value, by the smallest result. In this case, my result is 4.11, 6.9, 274. Then I will divide them all by 2.74. So this one is going to be a 1. 4.11 divided by 2.74. That is exactly 1.5. 6.9 divided by 2.74. That is also 2.5. Well, 50, 52. Okay, so I got my coefficients, right? Or my subscripts. So theoretically, this molecule should be C. All right. Okay. So, okay. So there was a technical problem. I lost my internet apparently in the middle of my recording. Okay. So let's continue. So we have C1.5, hydrogen 2.5, and oxygen 1. But obviously, you never seen a formula with decimal places, right? So that means that we have to time everything by a number that makes it a whole number. So in this case, would be C3H 2.5 times 2, 5, O2. So that would be my empirical formula. Okay, that would be my empirical formula, C3H5O2. Now they're asking me to determine the molecular formula. So you want to determine the molecular formula, then you have to do this. You have to get a factor. Normally, I call it theta factor. So you have to determine first the molecular weight. of your empirical formula. Okay? In this case, my empirical formula is this. So it's C3H5O2. If you get the molecular formula, it is each carbon is 12, 12 times 3, 12 times 3, 36, right? One hydrogen, right? Hydrogen is 1 times 5, 5. Oxygen, 16 times 2, 32. What is the molecular weight of my empirical formula? It is 35, that would be 41, 41, 73. 73. So the molecular weight for my empirical formula is equal to 73 grams per mole. So this theta factor is going to be equal to the given molar mass divided by the molar mass of the empirical formula. In this case, what is the given mass of the given mass that they get, right, from the problems? 146 grams per mole. What is the molecular mass of the empirical formula? 73 grams per mole. So if you divide this, 2. So that means that your factor is 2. Your empirical formula was C3H5O2, but this one you're going to time it by 2. So C6H10O4. That is your molecular formula. Okay, so I will do more problems on this, so don't worry. I mean, definitely I'm going to be doing more on the videos for solve problems. Okay, so let's go back to the okay. Empirical formula, yeah, that's the answer. C3H5O2, molecular formula C6H10O4, which is exactly what we what we had in our calculation. Okay, chemical equations. Now, this is a very important part of this part of this chapter is how to write a chemical reaction. Anytime that you see a chemical reaction will be divided into two sections. You can see here on the left side, which are the reagents, and the right side, which are going to be the reactants. Right? So as you can see it right here, reactants and products. Yep. So they're divided by the arrow. The arrow is telling you that, for example, ethanol and oxygen react to produce carbon dioxide and water. What are these coefficients? Those coefficients are the stoichiometric coefficients. How do we get them? We get them by balancing the equation. We have to balance a reaction, okay? So that comes later. But for now, let's just like focus on the structure of a chemical reaction. In most of the cases, you will see the state. For example, if this water is liquid, you will see this one parenthesis L. That's the correct way how to write chemical reaction, L. Carbon dioxide is a gas, so you will see this carbon dioxide with a G that stands for gas, right? Oxygen is a gas, so most likely you will see this one with a G as well, with a representing that you have a gas here. Ethanol is a liquid, so most likely you will see an L there. Okay? So, but the main structure of a chemical reaction is this: like reactants on the left, products on the right. They are separated by the arrow. And then if you have multiple reactants, you will have separated them by a plus. Multiple products also separated by a plus. Is it always going to be 2 reactants, 2 products? No. You can have 1 reactant, 10 products, or 10 reactants, 1 product, or 2 products. So that number really varies. Okay? Reactants are only placed on the left side of the arrow, or products are only placed on the right side of the arrow. The equation is balanced, right? So that's something in this particular case, they're giving you the balance equation. They are not always going to give you the balance equation. You have to work you have to do the work for to get the balance equation. So, but what are these coefficients telling me in a chemical reaction? They are extremely important. That's why That's why doing or balancing an equation is the first step and is basically the most crucial before you do a stoichiometric calculation. This reaction, how I read it, it would say like 1 mole, right? Because if there is no number, I should understand that this one is 1. 1 mole of ethanol react with 3 moles of oxygen to produce 2 moles of carbon dioxide and 3 moles of water. Okay? So that's what you read. So these stoichiometric coefficients, they really represent the number of moles that are invested in a chemical reaction. The balance equation, I mean, that's those coefficients. That's exactly what we are going to do. I mean, the balancing of the equation. Okay? So here, let's do it by doing practice is the best to do. Okay? Let me see. So it's calcium oxide plus carbon give you carbon carbide plus CO2. Okay, they asked me to balance this equation. So you have to go by trial and error. Trial and error is maybe the most efficient and it works. Later on in chemistry 2, oh no, even later, I mean here in this class, we will see how to do another method. But right now we'll do trial and error. Okay? So normally you start by metals. You start balancing metals, then you follow with no metals. Then the last one, you always do oxygens and hydrogens. Okay? So that will be more or less the sequence that you have to follow to do the balance. In this case, what are my metals? Calcium is my metal. I have oxygen, carbon, calcium, carbon, carbon. Right? So calcium is my metal, the first one. One calcium, one calcium. So my metals are balanced. No metals, I have carbon. One carbon here, two carbons here. Okay? So something that is very important for you guys to know that whenever you balance equation, you are only allowed to add coefficients in front. Don't erase subscripts. For example, oh, I have 1 and 2. Okay, so it's better if I just erase these 2. So now I have 1 and 1. No, you're not allowed to erase subscripts. So you see a 2 here, that 2, according to the definite proportions, right, from the previous chapter, the law of the definite proportions, you cannot erase that 2 because this molecule is CaC2, so you cannot change that. So what I can do is add coefficients. So I will do a 2 in front. So now I have 2 carbons, 2 carbons, 1 calcium, 1 calcium. What about oxygens? Oh, actually, no. I have here one carbon and another carbon here. So 2 plus 1, 3. So it's really 3 carbons that I have to put here. Okay. Now the last one is, I'm done with non-metals. Now I have to do oxygen and hydrogens. I don't have hydrogens, so I have to focus only on oxygens. 1 oxygen, 2 oxygens. Okay, so by doing this, I have to change this now. 2, right? Because I have 2, now I have 2 oxygens, 2 oxygens. 2 and 2. Now, but by doing that, I balance the oxygens, but now I destroy my balance of the calcium. Now I have 2 calciums, 1 calcium. Then you have to go back. So that's why this method is called trial and error, because most likely you will have to go back and rebalance it until you find the right balance of the equation. So for example, here, 2 calcium. Now by adding that 2, I cannot add the 2 here. No, that's not allowed. You're not allowed to erase or to add subscripts. You are only allowed to do coefficients. 2 calciums, now 1 calcium. I change that again. But by doing this, I'm changing the number of carbons. So how many carbons? 2 times 2, 4 carbons here, plus 1 carbon here. That means that I have 5. So now this number has to change. And I think I'm all set now. Okay, so now let's do a final accounting. 2 calciums, right? 2 calciums here, 2 calciums here. Carbons, 5 carbons here on the left. 2 times 2, 4. 4 plus 1, 5 carbons. Good. 2 oxygens, 2 oxygens. That means that my reaction is balanced. Okay. So another example. Let me see. Here there is a good one. It's kind of long. but let's see. Uh, yeah, I can do that one from the book. Calcium hydroxide plus phosphoric acid to produce water liquid. Well, I'm omitting the Ca3PO4 2. Okay, so actually I'm going to use this example as a to show you the strategy, a shortcut. Okay, so same thing, metals, non-metals, oxygen, and hydrogens. Okay, so who are my metals? Well, my only metal here is calcium, I believe. Yes, 1 calcium, 3 calcium. So theoretically, I have to do the 3 here, right? Make sense? Okay. So what else? So after that, I have to do non-metals. But here is the trick that you guys can use. Um, phosphorus is right here. That's my only source of phosphorus. And phosphorus is also right here. So instead of balancing phosphorus and oxygen separate, what I'm going to do, I'm going to balance phosphate. So I will say 1 phosphate here, 2 phosphates here. That's also something you can do. They're totally entitled to do that. You can group the elements as long as they are exactly the same. PO4, PO4. 1 PO4, 2 PO4s, then coefficient here. Now I have 2 phosphates balanced. Now I do the oxygens and hydrogens. Well, that's separate. But remember that you don't count those oxygens, right? So because you are using them for phosphates. So how many oxygens do I have? I have 3 times 2, 6 oxygens. And here, don't count these, right? Because those are phosphate. I have only 1. So I have to add 6, right? To make it 6 oxygens. Okay. 3 calciums, 2 phosphates, 2 phosphates. Now I have to do the hydrogens. 2 times 3, 6. 6 hydrogens here. 2 times 3, 6 hydrogens here. Total, 12 hydrogens. What about here? 6 times 2, 12. So they are all balanced. 3 calciums, 2 phosphates, 2 phosphates, 6 oxygens, 2 times 3, yeah, 6. 6 here, 6 and 6, good. 12 hydrogens, yeah. 2 times 3, 6. 2 times 3, 6. 6 plus 6, 12. 6 times 2, 12. So the reaction is balanced. Okay, so that's another trick how to get the balance of equation by grouping. You are grouping the elements. All right. What would be my option? The answer from that problem would be 2, should be this one, option number 2. That one should be the correct answer. Yes. Or you can use the other one. I mean, normally you don't use fractions. Yeah, 2.5. I mean, there is nothing wrong with using fractions or decimals, but you can do that as well. That one is also another one. I mean, you can use multiples of the same coefficient. Okay, so number of molecules, the number of molecules is conserved. Yeah, the numbers of the molecules, like those subscripts, subindex. Coefficients tell you how much of each substance you have. Atoms are not created nor destroyed. That's why you have to balance each side, because if you have 5 atoms of carbon on the left, those 5 atoms of carbon should remain on the right. Right? So that's really what is true regarding the balance of the equation. Okay. That's very important. Please read these instructions. Subscripts must not be changed. You cannot change subscripts. Okay. Stoichiometric calculation. Okay, so now we are ready for the stoichiometric calculations. So stoichiometric calculations is really chemical equations that can be used to relate the masses of reactive chemicals. So there is different types of stoichiometric calculations you can do. You can do mole-mole stoichiometry, you can do mass-mass stoichiometry, and you can do mole-mass or mass-mole stoichiometry. What do I mean by mole-mole, mass-mass? So what I really mean is, like, remember that at the beginning I was saying that you get data, information, and you are asked for something. So that's exactly what I'm trying to say. I'm given the information in mass, and they are asking me the product about mass. Okay, so that I will call that a mass stoichiometry. The information they give me is moles, and they want me to find out moles. Moles and moles, that means it's a mole stoichiometry. They give me information about moles, and they are asking me about mass. Okay, so that means that it's a mole mass stoichiometry. So you always have to find, that's why at the very beginning, the first slides was about how do I find what I'm given and what I'm being asked for. Right? So please be very careful with that type of methodology. The first thing you have to do with a chemical reaction, balance it. Make sure that it's balanced. Not all the reactions are balanced. So if you have to balance it, balance it. Convert the known mass of the reactants of product, convert the known mass of the reactants or product to moles. Yeah, there's different type of strategies to approach. Here they're asking you to convert everything to moles. Yeah, sometimes it is easier to go to moles, but if the question is asking you for result in mass, well, you rather stay as mass, right? So we will see how we do this particular problem. Consider the following reaction, right? So I have phosphorus, ignore those parentheses, plus 5 oxygens give you 2 of diphosphorus pentoxide. Okay, so okay, so that problem tells me 6.25 grams of phosphorus, right? What mass of oxygen? I'm gonna keep that on the side. I'm gonna use this example for my lecture right now. Okay, so let's say that they are asking you for the first case, mole stoichiometry. Okay? So I see that my equation or my reaction is balanced, right? Because 4 phosphorus, 10 oxygens, 10 oxygens, balanced. There's no problem with the phosphorus. They are all good. So you always will have what I call a reference line. Okay, and the reference line, you have to do it based on the question. So for example, they tell me the reaction occurs if, let's say, like how many moles of diphosphorus pentoxide are produced by 3 moles of oxygen. Okay, that's the question. How many moles of the product are produced by 3 moles of oxygen? So I can really see that they are giving me, what information are they giving me? They're giving me moles. That's information. What are they asking for? They are asking me more for how many moles of the product. So I'm right now in front of a mole stoichiometry. They give me moles and they are asking me for moles. So this is mole ratio. Based on that is that I'm going to create my reference line. What is the reference line? The reference line is going to be moles. Okay, so they want me moles, I will give them moles. According to the equation, this one is a 1. 1 mole of phosphorus reacts with 5 moles of oxygen to produce 2 moles of diphosphorus pentoxide. 1, 5, 2. It's exactly the same number of the coefficients. Why in moles? Because they're asking me for mole ratio. If they ask me for mass ratio, I will put all this in mass, in grams. If they ask me mole mass ratio, I will put this in moles and this one in mass. Okay, so you have to adjust depending on the problem. Okay, now here is your problem, the problem line. The problem line is about how many moles of diphosphorus pentoxide, how many moles of phosphorus pentoxide, right? That's your unknown, are produced by 3 moles of oxygen. 3 moles of oxygen. Are they saying anything about phosphorus? No. In this particular case, they are not telling me anything about phosphorus, only about oxygen and phosphorus pentoxide. Good. So now that I have this set up, I will just do a proportion. 5 moles of oxygen, right? 3 moles of oxygen equal 2 moles of diphosphorus pentoxide X. If you clear on that, that will be equal to 2 moles, 3 moles of oxygen divided by 5 moles of oxygen. Moles of oxygen will cancel out. 2 times 3, 6. 6 divided by 5, that would be 10, 1.2. That will be my result, right? I mean, you can do the calculation, but it should be 1.2. Yes, right? My answer will be 1.2. So theoretically, if I combine 3 moles, right, 3 moles of oxygen, right, I should expect 1.2 moles of phosphorus pentoxide. Do I have to be giving everything? No, you don't have to be giving everything. For example, they didn't give me any information about P4, but I don't need it. I need only one reference point and one question point, right? The question and the reference. That's all I need. What if they give me everything? Well, that's separate. That's called limiting reagent. That's coming later. Right? So just be careful with this, with particular technique is that mole ratio. Okay, now the next one. The next one, I'm going to use it from the problem. The problem is how many grams, from the slide, from the PowerPoint slide, how many grams of oxygen are needed to produce, to react, sorry, to react with 6.25 grams of phosphorus. Okay, so this problem is how many grams, right, of oxygen are needed to react with 6.25 grams of phosphorus. Okay, same setup. P4 plus 5 oxygens give me 2P2O5, right? So that's the reaction. So I always need to have my reference line and my problem or question line. Okay, my reference and the question. In this case, what are they telling me? They are asking me how many grams of oxygen. So that is grams or mass, right? And what information are they giving me? They're giving me mass. So I'm in front of a mass stoichiometry or gram stoichiometry, right? Because they're asking me for grams and they give me grams. So this is a mass. This is no mole. This one was mole. This problem now is mass. Okay, so now if I have mass, that means that my reference line has to be in mass. How do I do that? Well, you do that by the molar mass, okay? Phosphorus, P4. What is the molar mass of P4? From the periodic table, I have that phosphorus is 31, but I have 4. 31 times 4, I could do it, but 124 grams, okay? 5 oxygen. Here I have 5 times 2 is 10, right? 10 times 16, right? Because 5 times 2, 10. So 160 grams. Here was 31 times 4, right? Here, well, here I will have phosphorus. How many phosphorus? 31 times 2, right? That's 62. Oxygen, 16 times 5, 80. Right? 16 times 5, just double check, 80, yeah. 80 plus 62, that's 142. But that 142 is under the 2, so that means 248. It's 244, sorry, 284. Right? 142 times 2, yes, so 284. One checkpoint that you can do, basically, you can see that everything is molar mass times the coefficient. Molar mass times the coefficient. Molar mass times the coefficient to molar mass times the coefficient. Okay? So double check according to the law of the conservation of mass. What is the beginning? The beginning I have 124 plus 160. I started off with 284 and I'm producing 284. So the law of the conservation mass should follow, right? Now, the question line. How many grams of oxygen, exon oxygen, are needed to react with 6.25 grams of phosphorus? Okay, are they saying anything about phosphorus, the P2O5? No, so then forget about it. So I do this correlation. 124 grams of phosphorus proportion to 6.24 grams of phosphorus equal to 160 grams of oxygen divided by X. Therefore, X is going to be equal to 160 grams of oxygen times 6.24 grams of phosphorus divided by 124 grams of phosphorus. I'm just clearing, right? Solving on X. Grams of phosphorus cancel out. So 160 times 6.24 divided by 124. 8.05 grams of oxygen. Okay, that's what I need, right? So 6.025 grams of phosphorus will react with 8.05. Right? That should be my answer, 8.05. That's the answer to this problem. Again, we will do many more problems on the videos that I post on YouTube. Okay. 8.07, yeah, well, it should be like a discrepancy, the last digit because of the rounding, okay? But that should be the mass of oxygen that I'm going to be producing. Methane react with oxygen with the air to produce carbon dioxide and water. Yeah, here is write the balance equation for each. Okay, so let's do that. Actually, that's a good example. It says methane react with oxygen. Methane is CH4. I'm going to write that here. CH4, right? React with oxygen in the air. Oxygen in the air is O2. There are some elements that are diatomic, like oxygen. In the air to produce means arrow, to produce carbon dioxide, CO2, and water. So we should be able to write chemical reactions from words. It says write the balance equation. Okay, if I write the balance equation, I see one carbon, 4 hydrogens, 2 hydrogens. Okay, so 2 hydrogens, then I do a coefficient here, 2. Now I have 4 hydrogens. Oxygens, I have 2 oxygens here, 2 oxygens here. I have 4 oxygens, I have only 2 here. Okay, so let's do a 2 here. Now this reaction is balanced. Okay? Ammonia reacts with oxygen, NH3 plus oxygen to produce nitrogen monoxide. Nitrogen monoxide is NO plus water. Let's balance this equation, right? Because definitely it's not going to be balanced. One nitrogen balanced. 3 hydrogens, 2 hydrogens. Okay, so here I have to use an artifact. What's an artifact? Is that I have to use 2 coefficients because there is no, this 2, 3, and 2 is impossible that I get them equal, right? This one will tell me by 2 and this one will tell me by 3. Why is that? Because 2 times 3 is 6, and 3 times 2 is 6, so I have 6 hydrogens. But that one is going to mess your nitrogens. Yes, it's going to mess your nitrogens. So you have here 2 nitrogens, and here you have 1 nitrogen. Therefore, I'm going to do that here at 2, right? 2 nitrogens. Now oxygens. Here I have 2 plus 3. 2 plus 3 is 5 oxygen. Here I have 2. Then I'm going to use here another artifact. So I need 5, right? So I'm going to use 2.5. Can I do that? Yes. But obviously, after that, I have to time everything by 2, right? Because I cannot have a 2.5 coefficient. But the 2.5 here works because I need 5 oxygens. 5 oxygens, but here I have 2.5 times 2 is 5. But I cannot report that like this. So really, the coefficient should be here 4 for ammonia, 5 for oxygen, 4 for nitrogen monoxide, and 6 in here. I'm just timing each coefficient by 2, right? 2 times 2, 4, 2.5 times 2, 5, 2 times 2, 4, and 3 times 2, 6, right? So that's what we need to do. Okay, so here, okay, so this is about what to do. I mean, I did already one mass, one mole stoichiometry. So here is extremely important, limiting reactant. I'm not going to take much of your time. I know this lecture is really long because of the amount of calculations. Limiting reactant is the reactant that is consumed first and therefore limits the amount of the products that can be formed. The term is which reactant is limiting, calculating the amount that the product that will be formed. Right? So what are we trying to say here in limiting reagent? Right? So is the amount here is with molecules is kind of complicated. I mean, I will see. For example, let's say that I'm going to the park today and then I have 5 pieces of bread and I only have 3 slices of cheese. How many sandwiches can I make? Well, assuming that I put 1 slice per bread, right? Per piece of bread. I can only make 3 sandwiches. Right? Are we clear with that, or we all agree? Even though I have 5 pieces of bread, I can only make 3 sandwiches because I only have 3 slices of cheese. So that means that my product is going to be limited by the number of cheese. So I would say that in this case, cheese is my limiting reagent. It's not that I don't, this one is the one that is going to say like enough, right? No more. I can have even 1,000 pieces of bread here. I have way more pieces of bread, but my number of sandwiches is going to be the same, only 3, because this one is the one that's going to dictate when is the end of the reaction. Here is called the excess, right? Reagent in excess. Excess reagent. This is in excess, right? Doesn't matter who dictates when the reaction ends. The limiting reagent. The limiting reagent is like, I'm done. That means that the reaction is done as well. Yep. So that's going to be important because, for example, you have a chemical reaction that they tell you A plus B, right, giving you C. In this case, they tell you 10 grams of A and 10 grams of B. How much are you going to produce? Then you're going to say like, okay, so now this time they give me 2 reference values. Which one should I do it? Should I do it with this or should I do it with this, right? So that's the question, right? Remember that in our previous example, we were saying like, you get a proportion and then you get your unknown. So here, if they give me 2, which one should I do it with? You will do it with the limiting reagent. Because remember, the limiting reagent is the one that tells you when the reaction ends. So if A is your limiting reagent, then your proportion has to be done with the limiting reagent. So don't forget about this one, not this one. You have to do it with this one because this is the limiting reagent. Yep. So whenever you're giving a problem, always try to find out who is your limiting reagent because without the limiting reagent, definitely you will not be able to, to get the right calculation. Okay? So these are just example about the molecule, how they react. But I think that the example of the bread and cheese is better than this. Definitely way better. Limiting reactants or limiting reagent is the amount of products that can form is limited by methane, right? So it's your limiting reactant. It's like the cheese and the bread. So in this case, your cheese is the methane, water is in excess, right? We cannot just simply add total moles. No, we have to decide which one is right, let's do it with actual molecules. Here they give us like A and B, but I would say like it's better if we do an actual reaction. So let's say that they are giving me, let's make water. And they tell me that how many grams, I'm going to show you in a second, how many grams of water are produced from 5 grams of oxygen and 2 grams of hydrogen. Okay, so I'm gonna open my camera now. Okay, I have this chemical reaction, is balanced, so don't worry about balancing. How many grams of water are produced from 5 grams of oxygen and 2 grams of hydrogen? Okay, so here I will proceed the same way, my reference line and my question line, right? This is a mass-mass ratio. I can tell that it's a mass-mass ratio because they're asking me about grams of water and they give me grams of the, right, grams of the reactant. That means that my reference line has to be in grams. Okay, so molar mass of H2 is 2. 2 times 2, 4 grams. Each oxygen is 16, 16 times 2, 32 grams. Water, molar mass is 18, 18 times 2, 36 grams. Okay. Now they tell me how many grams of water, okay, water, are produced from 5 grams of oxygen and 2 grams of hydrogen. Now they're giving me 2. So I have to find out who should I do the proportion with, right? I know that I definitely have to use this, but I don't know if I should pair this with oxygen or should I pair this with hydrogen. Then we have to determine the limiting reagent. How do I determine the limiting reagent? Let's forget about the water. We're just debating between these two. Who is the limiting reagent out of the hydrogen and the oxygen? So what you are going to do is just randomly take any, okay? So I'm going to write it right here. It's exactly the same setup. Okay, it's exactly what we had before. I'm just forgetting about the water part. I'm ignoring that part. So I'm going to ignore one, okay? So I know that I have 5 grams of oxygen, but I'm gonna ignore it. Why do you ignore oxygen? Can I ignore hydrogen? Yes, you can do either way, doesn't matter. You're going to do a second unknown, Y, okay? An unknown Y, Y or W, whatever. So I'm gonna determine the amount of Y that I need. So 4 grams of hydrogen proportional to 2 grams of hydrogen equal to 32 grams of oxygen, Y grams of oxygen. Okay? If you solve on Y grams of oxygen is going to be equal to 2 times 32 divided by 4. That is 816 grams. Okay? So that means that 2 grams of hydrogen need 16 grams of oxygen. Okay, is it clear? This 16, that calculator goes here. Okay, here's what you have to ask, right? So I need 16 grams of oxygen. I have, how many do you have? 5, right? Because you're given 5 grams of oxygen. What is your conclusion? I need 16, but I need 5. Sorry, I have 5. I have less than what I need. If I have less than what I need, then this guy is the limiting reagent. Oxygen is my limiting reagent. Okay? That's the way how you will determine it. So what about if you have more than what you need? If you have more than what you need, then that means that it's not the limiting. That would be the excess reagent, excess reagent. So, but in this case, I have less. If you have less, if you have more than what I need, then it's going to be the excess reagent, which is not the case for this, right? So in this case, I don't have more, I have less, because I need 16 grams and I have 5 grams because the problem is telling me that I have 5 grams of oxygen. Or is it gonna be the same scenario if I switch it to hydrogen, right? Because here I put Y on oxygen, but if I put Y on hydrogen, I'm going to get the same? No, you will get the opposite because you can only have one limiting reagent. It's impossible, you cannot have 2 limiting reagents. Okay? So this is the idea for limiting reagent, how to calculate it. So now that I know, right? Now that I know that oxygen is my limiting reagent, then this calculation will be done with this guy. What about this? Or forget it, because hydrogen is excess, right? Excess reagent. This one is my limiting. I always work with the limiting. So if I work with the limiting, good. So I will have 32 grams of oxygen, right? Proportional to 5 grams of oxygen, equal to 36 grams of water divided by X grams of water. Therefore, X grams of water will be equal to 5 times 36 divided by 32. Okay. If we do that, that would be 3 times 36 divided by 32, 5.63 grams of water. That should be your answer to your question. But you see, it's longer. Longer because you have to determine first the limiting reagent. Once you determine the limiting reagent, then is when you can finally do your proportion. Here I had two options. So I had to figure out which one was the excess, which one was the limiting. I found out that this one is the limiting. Then I do my proportion with the limiting reagent. Forget about the excess. The excess, you don't care about the excess, right? Okay, so let's continue. Now you guys know how to do limiting reagent. Once again, more examples will be on the solve problem videos. Okay, so exercise. Okay, now let's just change that. I mean, A and B examples, I mean, they're good, but I mean, they're not the most ideal. Percent yield. Percent yield is an important indicator of the efficiency of a particular lab or industrial reaction. There are obviously, for example, I'm sure that Bristol Myers or Roche or any of these Johnson and Johnson, like for example, these chemical pharmaceutical companies, they want highest efficiency, right? The percent yield. So remember, nothing in nature is 100% efficient, right? So even a chemical reaction never is going to reach 100%. So for example, in the previous problem that I did, how much should I be producing of the product? So theoretically, right, from this example, theoretically, I should be producing how much? 5.63. Do you think that that's going to be in real life? Am I going to be producing 5.63 grams of water in real life? No, this one is my theoretical yield. This is on the paper. On the paper, I will get that. But in practice, if I go to the lab, will I get exactly 5.63 grams of water? Never, never. That's why they came up with that idea of percent yield. So that would be the actual yield, that's experimental yield, divided by the theoretical yield times 100. That's gonna be your percent yield. Okay? So you calculate that, but obviously the percent yield is gonna be given. What mass of phosphorus is needed to produce 85 grams? 85 grams if the reaction has a 64% yield. Okay, so let's do this problem, and that will be the last one for this chapter. Okay, so well, have it there. So consider, so the problem says is P4 plus 6 fluorines, PF3, right? They tell me what mass of phosphorus 4 is needed to produce 85 grams of PF3 if the reaction has a 64.9% yield. All right. This is the chemical reaction. What mass of phosphorus, P4, right, do I need to produce 85 grams of PF3 at 49? Okay, so this one is what I want to get. This one is going to be my experimental. Okay, whatever I get here is always going to be theoretical. Okay, theoretical is always whatever I do my reference question line, they're always going to be theoretical. The experimental is what I want. So I have to get the percent, I have to find out the theoretical. Percent yield is equal to experimental divided by theoretical times 100. Okay, that's the formula. Percent yield, 64.9. Okay, I know that from here. Equal to experimental. I want this. I want this as experimental. 85 grams of PF3. What is the theoretical? That's what I want to find out. Why do I need this? Because I need to put this in here. Right? I need to put that in here so I can find out how many grams of P4 do I need. So theoretical, that would be equal to 85 times 100 divided by 64.9. I'm just solving on theoretical. I'm just clearing theoretical. 85 times 100 divided by 64.9. That's equal to 130.97 grams. Okay. Of what? Of PF3. Okay. So now, why did I do that? Because I need that for this part. This part has reference, right? And then question. What mass of P4, mass, to produce mass? That means that I'm in front of a mass stoichiometry. Mass stoichiometry means that my reference line should also be in mass. So mass will be masses, molar mass. Phosphorus 4, each phosphorus is 31. 31 times 4, 124. Fluorine. Do I need to do fluorine? Well, let's do it, but I don't need it really because the problem is not about fluorine at all. It's only about P4 and PF3. But let's do fluorine. Each fluorine, according to the periodic table, weighs 19. 19 times 2, 38. 38 times 6, 228. Okay. Here, three fluorines, 19 times 3, 57, plus phosphorus 31. This is 88. 88 times 4, 352. Which makes sense, right? Because 124 plus 228 is 352. So it agrees with the law of the conservation of mass. So what mass of phosphorus do I need, right? Do I need to produce 85%, right? But they want that experimentally. So, but experimental, you cannot plug this in. No, you can't do that. Why? Because this is experimental. You cannot put experimental value on your reference and question line. You have to put it theoretical. That's what we calculated, that I want 130.97 because your reaction is only 65% yield. So if you really want to get 85, you have to aim higher because your yield is relatively low, 64. Yep, so I'm gonna put that 130.97 grams here. So now I'm going to match these two guys, right? So 124 grams of phosphorus, X grams of phosphorus is equal to 352 grams of PF3 divided by 130.97 grams of PF3. Okay, X is going to be equal to 124 times 130.97 divided by 352 point, no, nothing, grams. X is going to be equal to 124 times 130.97 divided by 352, 46.14 grams of what? Of phosphorus. That is what you should be making react so you can get 85 grams experimental, because that 46 is aiming 130 theoretical, but that theoretical is, you're not going to get that theoretical because you only have 64.9% yield, right? So let's go double check. 46.1, great. So see 46.1 grams of P4. I will do more problems on this. Please check on the solve problems, solve problem folder on Blackboard. Let me know if you have any questions.